This video is talking about overfitting. And so we've done a lot of things in this course. We've built a bunch of different learners, a bunch of different machine learning models, and we've played with options, and we know a bunch of performance metrics, right? We talked about a bunch of different performance metrics, and we only sort of scratched the surface. There's even more than we talked about, but you have a way of judging how good your algorithm was applied to the data, and we have different ways of doing that. We have our cross validation, we have our test data sets, and our training data sets, and so when we talk about overfitting, we're actually talking about a model being almost too good. And what I mean by that is, so say we create a model, and it fits our data perfectly. So say we have 1,000 data points, and it fits those 1,000 data points perfectly, and then we add a new data point, 1,001. Well, depending if we've overfit or not, we we may actually have a poor performing model as far as our new data point goes. And let me start off by kind of drawing a typical linear regression, because it's easy to show with linear regression, and there's another type of regression that we'll go over. You won't have an assignment due in the course using it, but this is really good to know, and it's a topic that comes up constantly in data mining and machine learning. So we've got let me change the color here. I'll use yellow. And let's go back to our real estate example, and so say we've got just a bunch of data points. And so what we've done so far is we drew our line of best fit, and there's an algorithm and a way to do that, and so that's supposed to be a straight line, but you get the idea. And so if we have a new data point, so you can see like half is above, and let me draw some more data points so we can really show that essentially half are going to be above and half are going to be below, and then we draw that straight line through it. So let's give another similar example. So that's a pretty good fit model, because what will happen is we get a new data point. So, and I'll do that in red. We have a new data point that comes along here, and we're not going to get it exactly, because we're gonna pick here. So based on our regression equation, we pick here, and we're off by just a little bit, not much, and so that's fine. We have a pretty well performing model. So I'm gonna introduce you to a technique it's non-linear regression, and you're not going to have to do any assignment on it. I just want you to sort of know the term. And so let's kind of give some data like we had last time. So we've got, this is kind of a little bit of a contrived example, but you can see that we've got a bunch of data points, and all those are supposed to be tiny little data point lines. And with our linear regression, what would happen is we would try to draw some line through here, and it would be a straight line, and then that'd be a good approximate fit, saying that straight line. What we can do is we can start to follow this a little bit. Hopefully you can see this in the video. We can create some really crazy equation that does that, and it follows the data perfectly. But the issue is that it's overfit. So if we get a new data point, it's probably not going to be very accurate from our model. And if we had used linear regression, we would have probably had a better chance of fitting new data, because what if the new piece of data is this? Well, so our purple is our overfit, and then we've got kind of a pink that's a linear regression. Well, see how far we are from the purple line? We've got a pretty fair amount of distance. So the purple is going to estimate a very inaccurate point. If we were to use this linear regression, because it's more generic, we get a better fit. And so that's what happens with overfit is your model isn't generic enough for new data. It fits your old data perfectly, but when you start getting in new data, it's overfit. Your lines, your J48 decision trees, all these different models, and there's a bunch of different ways to describe it. And I'm kind of using the regression to really drive the point home because it's kind of easy to conceptualize. Some of the decision trees are a little harder to understand how they would be overfit. But we have our linear regression, and that tends to work out pretty well as opposed to other regression types because it's not overfit. It's much more general. And so I'm going to do a little bit of math here. I don't want to scare anybody. You're not going to get tested on any of this math, but I want you to remember some of your equations here. And from algebra, you had your y equals mx plus b. We've talked about that before. Y equals mx plus b, and that's a linear equation. That's kind of you have your slope and your y-intercept, and that's just going to be a straight line, right? Just like we have here. In kind of the context of data mining statistics, when we create these linear regressions, we don't have a perfect line, right? We create a perfect line, but our data doesn't follow a perfect line. So they write it in a slightly different way. So let's write it as y equals mx plus b, and so that you're used to that, plus some error term, e. What that error term, it basically holds every single thing we haven't accounted for. So let's go back to our real estate example. And remember, we just did price per square foot. And as square footage increased, our price increased. Well, I initially told you ignore kind of the extra things. Ignore the zip codes. Ignore the quality of the house. Ignore all the other things that kind of make the data all over the XY coordinate plane and give it all that variance. But now we're not going to ignore that. We're saying, okay, we're gonna look at it and we're gonna lump it all into this single error term. And what happens when you start to overfit a model? You're trying to guess this error term, and fundamentally, you don't know the error term. So if I only took two things into consideration, I just took the square footage and the square footage and the price, I have data on that. If I were to say, okay, let me try to figure out the zip code, well, we don't have any data on the zip code. We can kind of surmise, we can guess that maybe these are from different area codes or zip codes or whatever, but we don't know. We don't have any data on that. So we just have to lump it up into this error term. And when we're creating our model, we have two parts. We have this part, and then we have this part. And this part is known as our, this is, when our model is off, we can fix this. So we call this our reducible error. Okay, and then this, we can't do anything about this. We just have to live with it. And so what we call this is our irreducible error, because we're unable to reduce this anymore. We just have to live with it. And so I hope that makes sense. I just want you to understand this from kind of a conceptual point, kind of from an intuitive approach, that we're going to have some equation, and we have data points that we can actually create an equation from. But when we start trying to follow these data points too closely, we're essentially trying to guess something that's fundamentally unable to, something that we can't fundamentally guess. It's this error term, and we just don't have the data for this error term. This is zip codes. This is the quality of the cabinets. This is how well they've maintained the lawn. This is every single other factor that we can't, that we just don't have data on. All we have data on is our square footage and our price. And so that's kind of kept in here. And so when we have a bad model based on our square footage and price, we can fix that model. We can go in and say, can we make this line fit a little bit better? Say our line, instead of this, maybe our line looked like that, and we say, okay, that line isn't very good. Let's try to fix that line. That's supposed to be a straight line. I hope you can. Let me see if I can use this little feature. Yeah, that's better. That's supposed to be a straight line. We can fix that. We can say, okay, that's not a very good line. Let's try to fix that. Let's make it to be something closer to that, right? To this green one. That's reducible error, and then we have irreducible error. When we try to build a model based on irreducible error, that's when we get a model that's overfit. We have a model that follows our previously seen data, and this is the term for well, I don't want to confuse you. There's a name for it. If anybody's curious, email me and I'll let you know the term. But basically, you have the term before that you've seen, or the data that you've seen before, and the new data that's presented. So I hope that makes sense. And it's a very important topic, and I would suggest looking up more on Wikipedia and anything else that you can kind of get some information on. Don't worry about the mathematics behind it. Just understand the intuition, because you're going to create some models, and you want to create the highest quality model as possible without overfitting.